Hello everyone, welcome back to RC Circuits. This is lecture number 9. So in previous lectures, we have seen mostly first order RC circuits, mostly the problems and the concepts also. So in this lecture, we are going to summarize all those concepts so that it will be good revision for us, and we will solve some more problems, and so that it will be we are comfortable with the more problematic approach also. So let's start now. So I will start with, so for intuitive analysis, the most important points you have to remember. This is for intuitive analysis only. I mean, if you want to draw the waveforms directly by looking at the circuit, then you should not forget these points that we can note down here, and then we can see to solve a problem what are the steps do we need to follow, and then we can also see for calculation purpose what are the formulas you should remember. It's not mandatory, but it is recommended so that you can easily solve a circuit with numerical approach also. I mean, to get the numerical values also. So first we will solve, we will write important points for intuitive analysis. So the first thing you should know is, if these all the points we have already discussed, but we are just summarizing here. So if finite current flows through a capacitor, then it starts charging or discharging. And if a constant current so finite and constant are both are two different things. A constant current is the same current always flows through the particular capacitor across the time for in the circuit, but a finite current can change. So at one instant the current will be at some value, and at another time instant it can be another value. So those two are different points. So if a finite current of positive value is flowing through a capacitor, then the capacitor will charge. But if the finite current flows out of the capacitor, then it will discharge. And similarly, for constant current flows through a capacitor, then the same thing will appear here, but charge or discharge will be in linear fashion. So this charging or discharging will be linear. And the next most important point is, if an impulse current flows through the capacitor, then there will be sudden change of voltage. So if you know these points, then you can easily draw a waveform across a capacitor, either voltage or current, intuitively. This is you can easily draw for first order circuits, that is for sure. And if a switching action happens, then at that switching instant, let's say if the switching action happens at t is equal to 0, then at t is equal to 0 plus. So that is at that particular instant, we have to assume omega tends to infinity, and at steady state omega tends to 0. So these we have discussed already, but we are summarizing now. And for solving a problem, you have to follow these steps to get exact like perfect steps, perfect answer. And steps to follow: steps for solving a problem. So first you have to find time constant for t greater than 0 if the switching action is happening at t is equal to 0. So find time constant, and there might be 3 possible cases for time constant. If it can be finite, it can be 0, it can be infinite. Infinite means continuously charging. This already we have seen one example also. And 0 means there will be sudden change. And finite means exponential behavior. So these are the possible cases for time constant. So that is the first step. And next step is draw the circuit at t is equal to 0 plus. So then you will get the intuitive analysis of what is the next step you have to do. I mean, so suppose at t is equal to 0, if you can able to determine if there is any impulse current flowing through the capacitor, or there is some finite current is flowing through the capacitor, so that you can intuitively analyze that, okay, now the capacitor charge will be exponential, or there will be some sudden change and then exponential. So those things you will know if you draw the circuit at t is equal to 0 plus and analyze at t is equal to 0 plus. And also then draw the circuit for t tends to infinity. And draw all the waveforms Vc and Ic across the capacitors. So these steps we have followed till now, and I think we are comfortable for solving the problems. So, and now for calculation purpose, suppose you have uh, solved with these steps and you got some equation or you got some waveforms, but if you want to find exact amplitude, suppose if you have impulse current, then what is the magnitude of the impulse current, and if there is some sudden change of voltage and it is going to 0, with exponential behavior of the capacitor, then you can also find the magnitude of the current at time instant. So those we can all solve with these calculations. For calculations, so let's say if the capacitor change has happened from V1 to V2, which implies there should be some impulse current, right, at that instant. So at t is equal to 0, there is impulse current. And the magnitude of impulse current should be C times the change in voltage, which is V2 minus V1. So this is how you can get the amplitude. And if the changes happen from V2 to V1, then you can, so here it is going from lower value to higher value. That's why you have got the magnitude as positive. Suppose if it is going from higher to lower, let's say V2 to V1, then you have impulse current I of t in negative direction with amplitude of the capacitor value times V1 minus V2. V1 minus V2 is negative. So this is the first one. And suppose a capacitor voltage starts from V2 and at steady state it reaches V1 and it discharges clearly. So since it is discharging, the current should be in negative direction. The current should be negative. So this is discharging, implies negative. But at steady state it is settling to some value, right? This voltage is V1 at steady state. So there should be no current at steady state. So it has to start from a negative value and then it should go to 0. So what is this amplitude? This amplitude should be the capacitor value times the change in voltage, which is V1 minus V2, final value minus initial value, divided by tau, the time constant of the circuit. This is only true for first order. Of course this you no need to remember, but if you remember it then you will get faster answers. So if you don't remember then it's fine, because you can easily get this current as C into dV by dt, and you have to write the V of t equation, then you have to differentiate that equation, then multiply with C and put t is equal to 0, so that you will get the initial value of current, that you will get same as this one. And suppose if it charges from V1 to V2, then this is negative current and you will get positive current. Charging implies positive current. So if you want to find the current magnitude at t is equal to 0, then so finally it will go to 0, that is for sure, because at steady state it is settling to V2, the voltage is settling to V2 and current should be 0, and current should be positive because of charging, and this value is same, C by tau times the change in voltage, V2 minus V1. And similarly this is for first order. Yeah, so these things you have to remember if you want to directly draw the waveform intuitively, and no need of magnitudes and nothing. So if you want to just draw the waveform, then these things you have to remember and you have to follow these steps and you will get the waveform. And if you want to find the magnitudes, then you just have to remember these 2 points, then you will also get the magnitudes. So let's solve some more problems today. So the circuit is given. The first step is you have to find the time constant for t greater than 0. So time constant for t greater than 0. So open circuit the current source. You have 2 capacitors are in series and a resistor of 2 ohms. So equivalently you will get a single capacitor of C1 C2 by C1 plus C2 with a resistor of 2 ohms in series. So tau is equal to C1 C2 by C1 plus C2 times 2. So this is finite. Now draw the circuit at t is equal to 0 plus. This is the second step. So for t is equal to 0 plus, you have 5 amps, 2 ohms, and these two will be short circuited. So all the current flows through these capacitors and this will be negligible because of short circuit across the parallel, and since finite current is flowing through the capacitor, there will be no sudden change. So this 5 amps will flow through both the capacitors. So Vc1 of 0 plus is equal to Vc2 of 0 plus is equal to 0 itself, which is the initial value, and IC1 IC2 both are 5 amps. Now at t tends to infinity, steady state, at steady state you have to assume omega is equal to 0. So both the capacitors will be open circuited and all the current flows through the 2 ohm resistor. So these two are high impedances are open circuit, and this current is 0 and this current flows through the resistor and you will get 10 volt here. And since this is C1 and this is C2 with high impedance, so assume you have a capacitor here with high impedance. Now this 10 volt is across both the capacitors and these two are in series now. So Vc1 of infinity, you will get 10 times C2 by C1 plus C2. Similarly, Vc2 of infinity is 10 C1 by C1 plus C2. And since time constant is finite, this will charge exponentially. So if you draw now Vc1 and Vc2, starts at 0, then it will go to 10 C1 by 10 C2 by C1 plus C2 at steady state. And similarly, this starts at 0 and will go to 10 C1 by C1 plus C2. Now if you want to draw the current waveforms, then since both are charging, the current should be positive for both the capacitors, and it should be same because those two are in series. So I'm just directly writing IC of t. So it should be at steady state, this is 0, and at t is equal to 0 plus it is 5 amps. So that's how you can get these waveforms, and this is a simple circuit. And yeah, now let's solve another problem. So we have a capacitor with initial voltage of 5 volt, and let's say this is C1, and you have a switch, and this is closed at t is equal to 0, and you have a resistor and a capacitor. And this capacitor has no initial voltage. So this is C2 R. Now the same concept. So find time constant for t greater than 0. So these two capacitors are in series and in series with a resistor. So you will get R times C1 C2 by C1 plus C2. So this is finite. And if you analyze at t is equal to 0 plus, then you replace the capacitor with initial voltage of 5 volt, and you have a resistor, and this is 0. So IC of 0 plus is 5 by R. This is finite. Implies C2 starts charging. So yeah. And for t tends to infinity, I'm taking that 5 volt out and open circuit that capacitor. Just for analysis purpose, and open circuit this capacitor. So this is C2 and this is C1. So for t tends to infinity, the current is 0, and F drop is 0 volt. Now this is Vc2, right? Vc2 of infinity. So Vc2 of infinity is you have 5 volt, and if you find that this complete is Vc1, so Vc1 of infinity is equal to Vc2 of infinity. So both the capacitors will go to the same finite value. So 5 times C1 by C1 plus C2, which is same as Vc1 of infinity. That's it. Now draw the waveforms. Vc1 of t. So Vc1 initially it is 5 volt, and it is going to, so this is discharging now. So at t is equal to 0 plus, you got a finite current of 5 by R, right? And it is flowing in this direction, right? Which means the capacitor C2 will charge in this direction, and the current is coming out of the capacitor C1. It means the capacitor C1 is discharging. So that is what you have got exactly. So it is at 5 volt and this starts discharging, and C2 is at 0 volt and it starts charging, and both will go to same final value. So this is also 5C1 by C1 plus C2. That is how this circuit will work. And if you want to draw IC1 and IC2, so for a capacitor I am assuming always IC1 is in this direction. Let's say this is Vc1, then IC1 is in this direction. If it is Vc1, then only you will get I is equal to C into dV by dt relation, if you assume this polarity. So but the current is coming out of the capacitor, right? But we have assumed Vc1 is in this polarity. It means IC1 should be negative, and since it is discharging, from that also we can say IC1 is negative. So this is T, IC1 of T, and this is negative, and finally this will go to 0, and this magnitude is just multiply the capacitor value C1 times the difference between these two, 5C1 by C1 plus C2 minus 5 times 1 by time constant. Time constant is these two are in series, right? So C1 C2 by C1 plus C2 into R. So that is the magnitude. If you want to solve this, then C1 times minus 5C2 by C1 C2 times R. So you will get minus 5R. That is the magnitude. And if you want to draw for IC1, sorry, IC2, so IC2 should be positive because it is charging. So this should be some finite value and exponentially decay to 0, and this value should be the capacitor value C2 by time constant C1 C2 by C1 plus C2 by R. I think this should be minus 5 by R. So C2 times C2 by time constant C1 C2 by C1 plus C2 times R, yeah, times the difference in voltage, I mean initial to final value, so which is 5 C1 by C1 plus C2. Then you will get C1 C2 C1 plus C2 will get cancelled out, you will get 5 by R. So that is the amplitude. So this is how you can draw all the waveforms. And let's go to one more circuit. So in this circuit you have a current source of 5 amps, 5 u of t, which means 5 amps is flowing through the circuit only at t greater than 0. For t less than 0, it is open circuit. Which is nothing but this switch is closed at t is equal to 0. So C2 C1 R. Now for time constant, open circuit the current source. If you open circuit the current source, then these two capacitors will come in series, which is in series with the resistor. So R equivalent is R, C equivalent is C1 C2 by C1 plus C2 times R. Now at t is equal to 0 plus, just pump that 5 amps and short circuit the capacitors. So through C1 no current will flow at t is equal to 0 plus. This is 0 amps. All the current will flow through the short circuit path. So this is C2, right? So IC2 of 0 plus is 5 amps. IC1 of 0 plus is 0. Now at t tends to infinity, if you open circuit the capacitor, okay, I'm sorry. So actually I'm sorry, I think this is correct only. Okay, so IC2 of 0 plus you will get 5 amps and IC1 of 0 plus you will get 0 amps, which means the capacitor C2 will start charging, right? But what about capacitor C1? Will it, how will it charge? Because there is no current flowing through the capacitor C1, right? So in this case, whenever this complete 5 amps is flowing through the C2, right, then it starts charging, then it will develop some voltage. If it develops some voltage, let's say 1 volt, then that particular voltage will come across this branch, right? So across this resistor it will come, then that particular current, let's say it is 1 volt and this is 1 ohm, then 1 amp of current will flow through the C1 at that instant and 4 amps will flow through the C2. Then the capacitor C1 will charge. So at t is equal to 0 plus, only the capacitor C2 starts charging. Immediately if it develops some voltage, then the capacitor C1 starts charging. That is how this circuit works. So for t tends to infinity, 5 amps, and both are open circuited. Now you are pumping a constant current source of 5 amps, but there is no way for the current to flow, and this is a violation, right? This is a KCL violation. So ideally, if you see these open circuit and no current should flow through the capacitors, but practically this is not possible because this is high impedance, because at steady state omega tends to 0. So these two are high impedances. So a high impedance is in series with some other impedance, then it is equivalent to that high impedance, right? So this is a resistor and this is high impedance. So equivalently you can represent it as a high impedance, which is C1. So 5 amps and a high impedance path and one more high impedance path. So there are two high impedance paths, and that impedance depends on C1 and C2. So now depends on C1 and C2, the current will divide at steady state. So IC1 of infinity is 5 times C1 by C1 plus C2, and IC2 of infinity is 5 times C2 by C1 plus C2. Yeah. If you want to draw the waveforms of voltage and currents, so better if you can draw the current waveforms first, because you have already the initial currents and final currents, right? So if you can draw IC1 and IC2 and then go back and uh, try to draw VC1 and VC2, then you'll get the idea. So for IC1, initially it is 0 and finally it is going to 5C1 by C1 plus C2, right? So in previous circuits, we have seen that all the steady state capacitor currents are 0, because finally the capacitor is charging to some final voltage and the capacitor current is 0. But in this circuit, the steady state capacitor currents are finite for both the capacitors. So this value is 5C1 by C1 plus C2, and IC2 is coming down from 5 to 5C2 by C1 plus C2. So let's say this is 5 amps, and from 5 to it is going down to 5 5C2 by C1 plus C2. So now see, the steady state currents are finite for both the capacitors, right? It is not finite, I mean it is constant, finite and constant. Which means if you pump a constant current through the capacitors, then it will charge linearly, which means it is not going the capacitor is not going to some steady state final voltage, it is going to some steady state final current, which means it is still in charging phase only. I mean there is no steady state for it. So let's say uh, so at this point it is going to steady state value, assume. So from this point, since the current is constant from this point, the capacitor will charge linearly, both. I mean, from here it should appear like this, right? And before that, let's analyze what will happen. So since both the currents are positive, then both the capacitor should charge, I mean, it should charge to some voltage, right? So it should not discharge. Both the capacitors should charge because the currents are positive. So I is equal to C dV by dt. Depends on the current magnitude. How the capacitor will charge will determine. So here the current is 0, so the voltage is 0, and then the current magnitude is increasing right here, but here the current magnitude is decreasing. So let's analyze this one. Since the current magnitude is increasing, the rate of change of voltage should increase, which means initially the slope should be lower, and when it goes to here, then the slope should be higher. I mean, initially it should charge and the slope should be parallel to x-axis, and then since the current magnitude is increasing, the slope should increase and it should be parallel to y-axis. I mean, initially it should be like this and parallel to x-axis, then it should go to parallel to y-axis. This is how the slope will increase. So approximately this is how the voltage waveforms look like. So till this point, the slope is lower here and the slope is higher. So till this point, the capacitor will charge like this, and after this one, the charging of capacitor should be linear, and this magnitude should be, this magnitude is nothing but dV by dt, right? So which is nothing but I by C, since I is constant and C is C1 here, so this slope should be phi by C1 plus C2. And similarly here, till this point it should charge depends on the current magnitude, but after this point, since the current is constant, it should charge linearly. Now C2 is initial current magnitude is higher, and if the time progress, then the current magnitude is decreasing, which means the slope should decrease. So initial slope should be higher and final this point slope should be lower, and this should charge because the current is positive. So this should be higher and this slope should be lower. This is higher slope, right? This is near to axis and this is near to x-axis. So this is how it looks like. And then from here it should charge linearly and it should go on increasing. So, and the slope should be this current magnitude by capacitor value, which is C2, and you will get phi by C1 plus C2. With this ramp rate, it should increase from here. So approximately this is how you will get the voltage waveforms and exact current waveforms. And if you write the equations for current, IC1 of t is equal to phi C1 by C1 plus C2 times 1 minus e power minus t by tau u of t. And if you want to find Vc1 of t, it should be 1 by C1 integral I dt from 0 to t. If you do that, you will get Vc1. And similarly, IC2 is final value plus initial minus final value times e power minus t by tau u of t. So Vc2 is 1 by c2 integral I dt. So this is how you can draw the waveforms. So this is some different circuit compared to the previous all the circuits, because in all the previous circuits the current steady state current is 0 and steady state voltage is some finite value. Even if the voltage is changing suddenly, but still the steady state value is finite. Steady state voltage is finite, which means the steady state current is 0. But here there is constant steady state current, right? So this should charge linearly even at steady state also. So that is how this circuit is different. Yeah. And so most probably try to solve the circuit in time domain itself, then only you will get to know how the circuit is behaving, how the capacitor is charging and discharging. So those things you can get to know only in time domain analysis. But if you stuck anywhere, then of course you can change to Laplace domain, and in Laplace domain you don't require any of these analysis. You can just convert the circuit into Laplace domain, then solve by circuit analysis, then you will get the answer, and then convert into inverse Laplace, then you will get time domain equation. So I think let's try for this. So convert this circuit to Laplace domain. So this is method 2. Laplace domain. Phi u of t is converted into phi by s, and r is r, and c1 is 1 by c1s, the impedance, and the impedance of c2 is 1 by c2s. So this is IC1 of s, and this is IC2 of s. So IC1 of s, if you want to find, then the total current phi by s times opposite impedance by total impedance, plus r. So phi by s times c1s by c1s plus c2s plus r c1 c2 s square. If you take the LCM and solve, then phi c1 by s times r c1 c2 s plus c1 plus c2. So IC1 of s is equal to phi c1 by, if you take r c1 c2 common, into 1 by s times 1 by s plus c1 plus c2 by r c1 c2. If you take r c1 c2 common, then you'll get this, and 5 by c2r times 1 by s into s plus, so this is 1 by tau, right? c1 c2 by c1 plus c2 is c equivalent, and if you multiply that with r, then you will get time constant. So this is simply 1 by tau. So IC1 of s is 5 by C2R times, if you take partial fractions for it, s plus 1 by tau, then put s is equal to 0 here, you will get 1 by 1 by tau, which is tau. Yeah, and if you put s is equal to minus 1 by tau here, then you will get 1 by minus 1 by tau, which is minus tau. So take tau common, tau is c1 c2 by c1 plus c2 times r by c2r times 1 by s minus 1 by s plus 1 by tau. Now if you convert into inverse Laplace transform, then IC1 of t is equal to 5c1 by c1 plus c2 times 1 minus e power minus 1 by tau. For 1 by s plus a, the inverse Laplace is e power minus at. This you have to remember. 1 by s plus a inverse Laplace transform is e power minus at u of t. So yeah, this is IC1 of t, and this should match our time domain analysis, 5c1 by c1 plus c2 times 1 minus e power minus t by tau u of t. So this is how you can directly get from Laplace transform. And similarly you can solve for IC2 also. And IC2 is simple, right? You are pumping 5 amps of current, 5 u of t, and you know IC1 of t. So you know this IC1 of t, and if you want to find IC2 of t, just subtract from the source current. So just subtract 5 minus IC1, then you will get IC2. So this is 5 u of t minus IC1 of t, you will get IC2 of t. And similarly you can find Vc1 of s and Vc2 of s also. So from here, if you want to get Vc2 of s, then multiply this impedance with the IC2 of s. So if you want to find Vc2 of s, then multiply 1 by sc2 times IC2 of s, then you will get Vc2, then convert that into inverse Laplace, then you get Vc2 of t. And similarly you can find Vc1 of t also. So Vc1 and Vc2 will get some complex equations that is not direct exponential and something else, right? It is some kind of behavior, and finally at some point, after some point, it is going to linear value. So that's how this circuit will work. Yeah, and similarly let's look at one more circuit. You have a source voltage of impulse value, let's say Vs times delta t, Vs times del of t, sorry. So this is R and C. For a series RC circuit, you are giving a impulse voltage, then let's see what will happen to this voltage or this current. Now at t is equal to 0 plus, at t is equal to 0, because del of t exists only at t is equal to 0. For t less than 0 and for t greater than 0, it is 0. It is only exist at t is equal to 0. And so only at t is equal to 0 you have impulse voltage, right? And this should be short circuited. So if you have impulse voltage and you are giving that directly to a resistor, then the impulse current will flow. So this is impulse current. So the magnitude of impulse current is IC of t is Vs del of t by R. So magnitude is Vs by R of that impulse current. Which implies sudden change of voltage across cap. So what is a sudden change? It should be so if you go back and remember, uh, this magnitude is the capacitor value times the change of voltage, right? If the voltage is changed suddenly, then the change of voltage, the difference of voltage times the capacitor give you this magnitude, right? So Vs by R should be equal to C times the change of voltage. Let's say this is some V0 and initially it is 0. So V0 you will get Vs by Rc. I mean, it will go to Vs by Rc. Now for t greater than 0, now you don't have this source voltage, right? You have the capacitor is immediately charged to Vs by Rc, and now you have simple RC series RC circuit with no independent sources. So now for this the initial voltage is Vs by Rc, and this capacitor will discharge exponentially. So this will discharge in 5 time constants. So 5 Rc. So Vc of t is Vs by Rc e power minus t by tau u of t. And if you want to draw the current, then IC of t, then you have positive impulse current. That's why the capacitor is charged to a positive value. It is increased from 0 to Vs by Rc, and this magnitude is Vs by R. And since it is discharging, which means the slope is negative, the current should be negative. It should go to 0, and this value is minus C by tau times Vs by Rc. Yeah. This is how this circuit will behave, and yeah. Yeah, this that's it for this lecture. And if you have any doubts, please comment down here and we will try to answer. So these are some good problems and good analysis. So in upcoming lectures we will try to solve some more complex and uh, best practice for our best problems for our practice. And if you like this video, please share to your friends. Yeah. Thank you.